Subscribe to the channel so you don't miss out on any of these videos. Imagine for a moment that all the mysteries of the universe, every black hole, every quantum particle, every ripple in spacetime, could be explained by a single equation. One elegant truth that ties together the vastness of galaxies and the minuscule dance of subatomic particles. This is not just some wild fantasy, it's the ultimate dream of physicists, mathematicians, and anyone who has ever looked up at the stars and wondered, why does the universe work the way it does? But here's the catch, we're not there yet. In fact, after decades of searching, we're still missing the one thing that could unify everything we know about the cosmos. This is the search for the theory of everything, and it's one of the greatest mysteries in science today. At the heart of this quest lies a paradox. On one hand, we have quantum mechanics, the mind-bending theory that governs the smallest particles in the universe. It explains why atoms exist, how electrons behave, and even the strange phenomenon of quantum entanglement, where particles can instantaneously influence each other across vast distances. On the other hand, we have general relativity, Einstein's groundbreaking theory that describes the universe on the grandest scales. It tells us how gravity works, why planets orbit stars, and how spacetime bends and stretches like a cosmic fabric. Both theories are incredibly accurate within their respective domains, but here's the kicker, they don't play well together. Try to combine them, and you get mathematical chaos. This clash becomes most apparent in extreme conditions, like the heart of a black hole or the first moments after the Big Bang. In these environments, both quantum mechanics and general relativity should apply, yet their equations break down. It's as if the universe is hiding something from us, some deeper truth that could reconcile these two pillars of physics. That deeper truth is what scientists call the theory of everything, or TOE for short, a single framework that could explain all the forces of nature in one fell swoop. Now, before we dive into the wild and complex theories attempting to solve this puzzle, let's take a step back. Why do we even need a theory of everything? Isn't it enough that quantum mechanics and general relativity work in their own domains? Well, the problem is that nature doesn't divide itself into categories. The universe doesn't care about our human-made distinctions between big and small. If we want to truly understand reality, we need a theory that works everywhere, from the quantum realm to the cosmic scale. So, where do we start? One of the most famous attempts to unify physics is string theory. At its core, string theory suggests that everything in the universe isn't made of point-like particles, but tiny, vibrating strings of energy. These strings are unimaginably small, so small that even our most powerful microscopes could never see them. But their vibrations determine everything we observe, from the mass of an electron to the force of gravity. In this framework, the universe isn't made of particles, but of harmonies, with each string playing its own note. What makes string theory so compelling is that it naturally includes gravity. In fact, it's the first theory to successfully merge gravity with quantum mechanics. But, and this is a big, but string theory comes with its own set of problems. For one, it requires the existence of extra dimensions beyond the three spatial dimensions and one time dimension we experience every day. According to string theory, there could be up to 10 or even 11 dimensions, curled up so tightly that we can't perceive them. While this idea is fascinating, it's also hard to test experimentally, which makes string theory difficult to prove or disprove. Then there's loop quantum gravity, another contender in the race for a theory of everything. Unlike string theory, loop quantum gravity doesn't try to unify all the forces of nature. Instead, it focuses on one specific problem, reconciling quantum mechanics with gravity. The theory suggests that spacetime itself isn't smooth and continuous but made up of tiny, discrete loops. Imagine zooming in on the fabric of the universe and seeing a mesh-like structure, where each loop represents a quantum of spacetime. This approach has led to some intriguing ideas, like the possibility that black holes might not destroy information but instead preserve it in some way we don't yet understand. Of course, these are just two of the many theories scientists are exploring. There's also supersymmetry, which proposes that every particle we know has a superpartner particle, an M theory, a more advanced version of string theory that could unify multiple versions of the theory into one. Each of these ideas has its own strengths and weaknesses, and none of them have been definitively proven. But perhaps the biggest challenge in the search for the theory of everything isn't mathematical or theoretical, it's practical. Testing these ideas requires experiments on scales that are currently beyond our reach. For example, probing the quantum nature of gravity might require a particle accelerator the size of our solar system. That's not exactly something we can build anytime soon. Still, progress is being made. Advances in technology, like the discovery of gravitational waves, are providing new ways to test the predictions of these theories. And as we learn more about the universe, from the mysterious behavior of dark matter to the strange properties of black holes, we're gathering the pieces of a puzzle that could one day lead us to the ultimate truth. What's at stake here isn't just a deeper understanding of the universe, it's a complete transformation of how we see ourselves within it. If we can find a theory of everything, it would answer some of the most profound questions humans have ever asked. Why is there something rather than nothing? What is the true nature of time? And perhaps most intriguingly, are we part of a multiverse, a vast collection of universes, each with its own set of rules? As we stand on the precipice of these discoveries, it's worth remembering that the search for the theory of everything isn't just a scientific endeavor, it's a human one. It's driven by our innate curiosity, our desire to understand the world around us, and our endless quest to uncover the mysteries of existence. This journey might take decades, centuries, or even millennia, but one thing is certain: the search itself is as awe-inspiring as the answers we hope to find. But what if the answer to the theory of everything is something we can't yet comprehend? After all, the history of science is full of moments where humanity hit walls of understanding, only to later leap over them with breakthroughs that redefined everything. Consider how impossible it must have seemed, centuries ago, to imagine the Earth orbiting the Sun, or how absurd it sounded to suggest that time itself could slow down when you move faster. These ideas were once unfathomable, but now they're cornerstones of science. Could the theory of everything be waiting on a similar leap, something so revolutionary that it challenges even the way we ask questions about the universe? One of the most intriguing aspects of this search is how the journey itself has revealed hidden connections between seemingly unrelated phenomena. For instance, in quantum mechanics, particles don't behave like tiny billiard balls. They exist as waves of probability until they're observed. This strange, observer effect, hints at a deep link between the universe and the act of measurement itself. Meanwhile, general relativity teaches us that gravity isn't really a force but the warping of spacetime by mass. These two ideas seem worlds apart, yet both fundamentally redefine our understanding of reality. The hope is that the theory of everything will not only unify these ideas but show us how they were always part of the same story. Yet, there's a growing camp of scientists who argue that our current approach might be the problem. Most of the efforts to find a theory of everything are deeply rooted in mathematics, relying on equations to describe the universe. But what if math itself is just a tool, a language we've invented to describe something that goes even deeper? It's possible that our reliance on equations is limiting us, much like trying to describe the color red to someone who's never seen it. Could there be a whole new framework, beyond math, waiting to be discovered? To complicate matters further, the universe might not even be governed by one unified theory at all. Some researchers speculate that the laws of physics, as we know them, might only be local truths, rules that apply in our part of the cosmos but not universally. Imagine if the fabric of reality changed from one region of the universe to another, with entirely different laws governing each domain. This idea, though speculative, would mean that the very concept of a theory of everything is flawed. Instead of one elegant truth, we might have to settle for a patchwork of explanations, each tailored to specific conditions. And then there's the wild card in all of this: consciousness. While the theory of everything is often framed as a quest to understand the physical universe, there's a growing realization that any complete understanding of reality must also account for the fact that we, as conscious beings, are part of the universe too. After all, what good is a theory of reality if it doesn't explain how we, the observers, fit into it? Some physicists believe that consciousness itself might play a fundamental role in the workings of the universe, possibly even influencing the way particles behave on a quantum level. If that's true, then the search for the theory of everything might also be a search for the nature of consciousness, a mystery that's as deep and puzzling as the universe itself. It's worth noting that this isn't just a scientific or philosophical question, it's also deeply personal. Every person who has ever stared up at the stars, wondering about their place in the cosmos, is participating in this quest in their own way. The search for the theory of everything isn't just about understanding the universe. It's about understanding ourselves, our origins, and our destiny. What could be more profound than that? But as we push further into this mystery, new challenges arise. For one, the universe is filled with phenomena that defy our current understanding, from the bizarre behavior of dark energy to the unexplained nature of time itself. Time, in particular, is a riddle that cuts across both quantum mechanics and relativity. In Einstein's universe, time is flexible, a dimension that bends and stretches depending on your speed and gravitational environment. In the quantum world, however, time is often treated as a static backdrop against which particles move. Reconciling these two perspectives is a critical part of the puzzle, and it may hold the key to unlocking the theory of everything. Some scientists have even suggested that time might not exist at all, at least not in the way we perceive it. Instead, time could be an emergent property, a byproduct of deeper, timeless laws of physics. If true, this would completely upend our understanding of reality, forcing us to rethink concepts as basic as cause and effect. Imagine a universe where the arrow of time is just an illusion, where the past, present, and future are all equally real. What would that mean for our understanding of existence, or for our sense of free will? Of course, this level of speculation can feel overwhelming, even dizzying. But it's also a reminder of why the search for the theory of everything is so exhilarating. It's not just about solving equations or proving theories. It's about pushing the boundaries of human imagination. Every new discovery, every unexpected twist, is a step closer to understanding the grand tapestry of existence. And yet, the search isn't without its critics. Some argue that the idea of a theory of everything is itself a kind of hubris, a belief that humans can somehow grasp the full complexity of the universe with our limited brains. Others worry that the focus on unification might distract from more practical scientific pursuits, like understanding climate change or curing diseases. These criticisms are valid, but they also miss the point. The search for the theory of everything isn't just about finding answers. It's about asking the biggest questions, the ones that challenge us to think beyond the ordinary and strive for the extraordinary. As we continue this journey, one thing is clear: the universe is far more mysterious and wondrous than we could ever have imagined. Whether we ever find the theory of everything or not, the quest itself is a testament to the power of human curiosity. It's a reminder that even in the face of the unknown, we keep asking, keep exploring, and keep reaching for the stars. The search for the theory of everything isn't just about the equations we write or the theories we propose. It's a reflection of our relentless drive to connect the dots. We are creatures who long to understand, and this quest is arguably the ultimate expression of that need. Every piece of evidence we gather, every paradox we encounter, and every boundary we push is a part of this grand, ongoing story. Think about the Higgs boson, often called the God particle. Its discovery in 2012 was hailed as one of the most significant achievements in modern physics because it confirmed the mechanism that gives particles their mass. But even that triumph didn't answer everything. It simply opened the door to new questions. The Higgs field is a cornerstone of the Standard Model, yet its properties remain puzzling. Why does the Higgs boson have the mass it does? What role, if any, does it play in linking quantum mechanics with general relativity? These mysteries linger, and they hint at something bigger, a deeper layer of reality that we have yet to uncover. In this deeper layer, theories like string theory, loop quantum gravity, and others continue to evolve. String theory, despite its elegant promise, faces major challenges when it comes to making testable predictions. It proposes that the universe's fundamental building blocks aren't particles but tiny, vibrating strings. Each string vibrates at a specific frequency, creating the properties of particles like electrons or quarks. But string theory also requires the existence of extra dimensions, far beyond the three spatial dimensions and one-time dimension we experience daily. These additional dimensions are hypothesized to be compactified or hidden in ways we can't directly observe, which makes the theory both fascinating and frustrating. On the other hand, loop quantum gravity takes a completely different approach. Instead of introducing strings and extra dimensions, it focuses on space and time themselves, proposing that space-time is not smooth but granular, made up of discrete chunks. According to this view, just as matter is made of atoms, space-time is composed of minuscule, indivisible units. If true, this granular structure could hold the key to understanding phenomena like black holes and the Big Bang, where general relativity breaks down. But like string theory, loop quantum gravity struggles with experimental verification, leaving it tantalizingly out of reach for now. Meanwhile, newer ideas are emerging, each as bold as the last. Some physicists suggest that the universe might not even be fundamentally mathematical in nature. Instead, it could operate on principles that our human minds aren't yet equipped to grasp. Imagine trying to explain quantum mechanics to someone living in the 12th century. They simply wouldn't have the intellectual framework to understand it. Similarly, there's a chance that we're in the same position now, looking at the universe through a lens that's too narrow to see the full picture. One particularly mind-bending idea is the holographic principle. This theory suggests that everything we experience as three-dimensional might actually be encoded on a two-dimensional surface, much like a hologram. If this is true, then what we perceive as reality is an illusion of depth, a projection of information stored in lower dimensions. This concept has been explored in the context of black holes, where the information about everything that falls into them is thought to be stored on their two-dimensional surfaces. Could the entire universe work the same way? If so, the theory of everything might not be about unifying forces but understanding how information and reality are interconnected on a fundamental level. Yet, for all our theories and hypotheses, we keep running into the same problem: testing them. Our experiments, no matter how advanced, are limited by technology, energy constraints, and even the very scale of the universe. To probe the deepest levels of reality, we might need tools or methods that don't yet exist, or we might need to completely rethink how we approach science. It's possible that breakthroughs will come not from giant particle accelerators but from unexpected sources, like studying the quantum behavior of biological systems or exploring the data paradoxes of artificial intelligence. And this brings us to another profound question: what if the theory of everything isn't something we discover but something we create? Perhaps reality is not a fixed puzzle waiting to be solved but a dynamic system that evolves as we interact with it. This idea, though speculative, suggests that the universe might respond to our questions in ways that are fundamentally unknowable. In this view, the search for the theory of everything is less about reaching a final answer and more about engaging in an endless dialogue with the cosmos. All of this paints a picture of a universe that is as mysterious as it is awe-inspiring. The deeper we look, the more we realize how little we know, and that's what makes this journey so thrilling. It's not just about solving equations or finding a neat, tidy theory that ties everything together. It's about embracing the unknown, challenging our assumptions, and daring to imagine what lies beyond the limits of our understanding. Even if we never find the theory of everything, the search itself is its own reward. Every step we take, every mystery we uncover, brings us closer to understanding not just the universe but our place within it. And maybe, just maybe, that's the real point: not the answers we find but the questions we ask, the connections we make, and the wonder we feel as we look out into the infinite unknown. The search for the theory of everything, at its core, is a reflection of humanity's endless curiosity and a testament to our relentless pursuit of understanding the cosmos. Yet, what if the very act of searching is shaping the answers we find? This is one of the most profound and unsettling ideas that modern physics has introduced: that the universe is not separate from the observer, but deeply intertwined with us. This concept, rooted in quantum mechanics, suggests that our observations may influence reality in ways we are only beginning to understand. In the double-slit experiment, one of the most famous demonstrations in quantum mechanics, particles like electrons exhibit wave-like behavior when not observed but behave like particles when measured. This bizarre phenomenon raises questions about the nature of reality itself. Is the universe deterministic and objective, or is it participatory and dependent on consciousness? If the latter is true, then the theory of everything may not just unify the forces of nature but also explain the role of the observer in shaping the universe. This brings us to the concept of quantum entanglement, another mind-bending cornerstone of quantum mechanics. When two particles become entangled, their states are interconnected no matter how far apart they are. A change in one instantaneously affects the other, defying the limitations of the speed of light. Einstein famously called this spooky action at a distance, and though it has been experimentally confirmed, its implications are staggering. How can information travel faster than light? And what does this tell us about the fabric of space and time? Some physicists propose that entanglement might hold the key to unifying quantum mechanics and general relativity, suggesting that space-time itself could emerge from these quantum connections. Emergence is another fascinating concept gaining traction in theoretical physics. Rather than assuming that the universe is built from fundamental, indivisible building blocks, emergence suggests that the laws of physics might arise from complex interactions at a deeper level. For example, just as the behavior of water emerges from the collective properties of its molecules, the fabric of spacetime might emerge from more fundamental quantum phenomena. This approach challenges the traditional reductionist view of physics and opens the door to entirely new ways of thinking about the universe. One such new way involves the idea of multiverses. The multiverse hypothesis suggests that our universe is just one of countless others, each with its own set of physical laws and constants. If this is true, then the theory of everything might not explain a single, unified reality but instead describe a framework that applies to all possible universes. This idea is supported by certain interpretations of string theory, which predict a vast landscape of possible universes, each corresponding to different solutions of the equations that govern the theory. However, the multiverse hypothesis comes with its own set of challenges. If other universes are entirely separate from ours and inaccessible to observation, can they ever be scientifically verified? Some argue that the multiverse is not a scientific theory but a philosophical one, as it cannot be tested or falsified. Yet others contend that indirect evidence, such as patterns in the cosmic microwave background radiation, could provide clues to the existence of other universes. As we grapple with these ideas, it becomes clear that the theory of everything is not just about physics, it's about philosophy, metaphysics, and even our deepest existential questions. Why does the universe exist? Why are the laws of physics the way they are? And why are we here to ask these questions? The search for the theory of everything forces us to confront these mysteries, reminding us that science and philosophy are not so different after all. The interplay between science and philosophy becomes especially evident when we consider the anthropic principle, which states that the universe must be compatible with the conscious beings observing it. Some interpretations of this principle suggest that the laws of physics are fine-tuned for the existence of life, raising questions about whether this fine-tuning is a coincidence, the result of a deeper necessity, or evidence of design. The anthropic principle also ties into the multiverse hypothesis. If countless universes exist, then it's not surprising that at least one of them has the conditions necessary for life. But even as we ponder these philosophical implications, practical questions remain. How can we test these theories? What kind of experiments could probe the deepest layers of reality? Some scientists are looking to black holes, where the extremes of gravity and quantum mechanics collide. Black holes are natural laboratories for studying these forces, and understanding their inner workings could provide crucial insights into the theory of everything. For example, the study of Hawking radiation, the theoretical emission of particles from black holes, might reveal clues about the quantum nature of spacetime. In addition to black holes, the early universe offers another window into the deepest mysteries of reality. During the first moments after the Big Bang, the universe was in a state of extreme density and temperature, where quantum mechanics and general relativity were equally important. By studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, scientists hope to uncover evidence of these primordial conditions. If we can decode this fossil radiation, we might glimpse the universe's quantum origins and bring us closer to a unified theory. Yet, for all our efforts, the theory of everything remains elusive. Some physicists even question whether such a theory is possible. Perhaps the universe is too complex, too vast, or too fundamentally unknowable to be captured in a single framework. Others suggest that our current scientific tools and methods are inadequate, and that breakthroughs will require entirely new paradigms of thought. This brings us back to the role of imagination in science. Throughout history, the greatest scientific revolutions, from Newton's laws to Einstein's relativity, have come not from incremental progress but from radical shifts in perspective. The search for the theory of everything may require a similar leap, one that challenges our deepest assumptions about the universe and our place within it. Ultimately, the search for the theory of everything is a journey without a guaranteed destination. But perhaps that's what makes it so compelling. In the end, the quest itself, the questions we ask, the discoveries we make, and the mysteries we uncover, might be the greatest achievement of all. The search for the theory of everything isn't just about understanding the universe on a scientific level. It's about redefining what it means to know anything at all. As we peel back the layers of reality, it becomes clear that each answer uncovers new questions, some of which challenge our most basic assumptions. Could it be that the universe operates on principles so alien to human intuition that they will always elude us? Or are we simply limited by our current methodologies and technology, awaiting the next breakthrough that will shatter our current paradigms? One intriguing possibility is that the theory of everything might not take the form of a traditional theory at all. It might not be a single equation scribbled on a chalkboard, or a tidy framework we can describe in textbooks. Instead, it could be a dynamic system, a living, evolving interplay of principles that defies static representation. Such a concept is difficult to grasp, especially since our scientific training emphasizes reductionism, breaking phenomena into smaller, more manageable components. But what if the universe resists being reduced? What if its true nature is holistic, emergent, and irreducibly complex? This is where ideas like loop quantum gravity and string theory push the boundaries of what we think a theory should be. Loop quantum gravity, for instance, doesn't just seek to merge quantum mechanics and general relativity. It reimagines spacetime itself. In this framework, space and time are not smooth, continuous entities but are composed of discrete quanta. Think of spacetime as a vast, intricate network of loops or threads, each one representing a fundamental unit of reality. This idea is as revolutionary as it is perplexing. How can something as continuous as time be made of individual chunks? And if spacetime is quantized, does that mean the universe has a smallest possible unit of distance or duration? String theory, by contrast, takes a radically different approach. Instead of focusing on particles or loops, it posits that the most fundamental entities in the universe are tiny vibrating strings. These strings, incredibly small and existing in dimensions beyond our everyday perception, produce all the particles and forces we observe through their different modes of vibration. Imagine a violin string. Depending on how it vibrates, it can produce different musical notes. Similarly, the vibrations of strings in string theory generate the various particles that make up the universe. But string theory doesn't stop there. It suggests that our familiar 3 dimensions of space and 1 of time are just the beginning. To make its equations work, string theory requires additional spatial dimensions, sometimes as many as 10 or 11. These dimensions are thought to be curled up or compactified, so tiny that they are imperceptible to us. This raises fascinating questions. Are these extra dimensions purely mathematical constructs, or do they have physical significance? Could they harbor entirely new laws of physics, or even parallel universes? Despite its elegance, string theory faces significant challenges. One of its biggest criticisms is its lack of testable predictions. While it offers a compelling framework, the scales at which its effects become noticeable are so minuscule, far smaller than anything we can currently probe experimentally, that verifying its claims is extraordinarily difficult. Critics argue that a theory that can't be tested isn't really science but philosophy. Proponents counter that string theory is a necessary step toward deeper understanding, even if direct evidence remains out of reach for now. Loop quantum gravity faces similar challenges. While it offers tantalizing insights into the quantum nature of space-time, it struggles to account for certain aspects of the universe, such as unifying all forces or explaining dark energy and dark matter. These mysterious components make up the vast majority of the cosmos, yet they remain largely enigmatic. If our theoretical frameworks can't incorporate them, can they truly be considered complete? The issue of dark energy and dark matter is another fascinating frontier in the search for the theory of everything. Dark matter, though invisible, exerts a gravitational pull that shapes galaxies and clusters. Dark energy, on the other hand, drives the accelerated expansion of the universe. Together, they dominate the cosmic landscape, yet their nature remains unknown. Are they fundamental aspects of reality, or do they hint at deeper layers of physics we have yet to uncover? Could a unified theory finally explain these cosmic puzzles, or are they separate mysteries altogether? This brings us to a deeper philosophical question. Is the theory of everything even discoverable by beings like us? Our understanding of the universe is shaped by our perspective as humans, our senses, our cognition, and our limitations. While we've developed tools to extend our reach, like telescopes and particle accelerators, these tools are still constrained by the boundaries of our imagination and the physics of our world. If the universe operates on principles that are fundamentally alien to our way of thinking, we might never fully grasp them. Yet, there's also reason for optimism. History shows us that humanity has repeatedly overcome seemingly insurmountable barriers to understanding. From the geocentric model of the solar system to Newtonian mechanics, every framework we've constructed has eventually been expanded or replaced as our knowledge grows. The theory of everything, if it exists, could represent the next leap in this progression, a synthesis of all we've learned and a gateway to entirely new realms of discovery. But perhaps the most profound aspect of this search is what it reveals about us. The fact that we're even capable of asking these questions, let alone pursuing answers, is remarkable. It speaks to the unique position we occupy in the universe, as beings capable of reflection, curiosity, and wonder. In seeking the theory of everything, we're not just trying to understand the cosmos, we're exploring our place within it. We're asking what it means to exist, to observe, and to know. The journey toward a unified understanding of reality is as much about the questions we pose as the answers we find. It's a process of constant reevaluation, adaptation, and growth. And even if the theory of everything proves elusive, the pursuit itself enriches our understanding of the universe and deepens our appreciation for its complexity. In the end, perhaps the ultimate truth lies not in finding a single, final answer but in embracing the endless quest for understanding. The endless quest for understanding isn't just an intellectual pursuit, it's a reflection of our deepest human instincts. From the earliest cave paintings to modern physics equations, humanity has always sought to make sense of the world. The search for the theory of everything symbolizes the pinnacle of that endeavor, the attempt to unravel the ultimate code of reality. But as we dig deeper into this grand puzzle, we find ourselves entangled in paradoxes and mysteries that challenge the very foundations of what we think we know. Consider, for example, the paradoxical relationship between quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles on the smallest scales, where probabilities reign, and uncertainty is a fundamental principle. General relativity, on the other hand, describes the universe on its largest scales, where the smooth curvature of space-time dictates the motions of planets, stars, and galaxies. Each theory is a masterpiece in its own right, with predictive power that has been tested and confirmed countless times. Yet, when brought together, they clash in spectacular ways. At the heart of black holes or the moment of the Big Bang, where both quantum effects and gravitational forces are extreme, our current equations break down. This conflict is more than a technical hurdle, it's a sign that our understanding of reality is incomplete. It's as if we're looking at the universe through two different lenses, each offering a partial view but failing to capture the full picture. The theory of everything, if it exists, would be the lens that unites these perspectives, allowing us to see the universe in its entirety. But how do we create such a lens? And what would it reveal about the cosmos and ourselves? One promising approach lies in the realm of string theory, which seeks to unify the forces of nature by proposing that all particles are manifestations of tiny, vibrating strings. These strings operate on a scale so small that their vibrations are imperceptible to us, yet their effects ripple throughout the universe. The beauty of string theory is its potential to harmonize the chaotic world of quantum mechanics with the geometric elegance of general relativity. By introducing additional dimensions of space, hidden from our perception, string theory creates a framework where these two seemingly incompatible theories can coexist. However, string theory is not without its critics. One major challenge is its sheer complexity. The mathematics of string theory is so intricate that even the most brilliant minds struggle to fully comprehend it. Moreover, string theory isn't just one theory but a family of theories, each with its own assumptions and implications. How do we know which, if any, describes our universe? Without experimental evidence to guide us, string theory risks becoming an elaborate mathematical playground, disconnected from physical reality. Another contender in the quest for a unified theory is loop quantum gravity. Unlike string theory, which introduces new dimensions and entities, loop quantum gravity takes a more conservative approach. It focuses on quantizing spacetime itself, treating it as a network of discrete units rather than a smooth continuum. In this view, the fabric of the cosmos is woven from tiny loops, each representing a fundamental quantum of space. These loops are not static but dynamic, constantly interacting and evolving in ways that give rise to the spacetime we experience. Loop quantum gravity has produced some fascinating insights, such as the possibility of a quantum bounce, replacing the Big Bang. Instead of a singularity where the laws of physics break down, the universe might have emerged from a prior phase of contraction. This idea not only resolves some of the paradoxes associated with the Big Bang but also suggests that the universe could be cyclical, with an infinite series of expansions and contractions. Yet, like string theory, loop quantum gravity faces the challenge of experimental verification. Its predictions operate on scales that are currently beyond our reach, leaving its status as a physical theory uncertain. As we grapple with these competing frameworks, it's worth considering whether our current approach to science might be limiting our progress. Both string theory and loop quantum gravity are products of reductionist thinking, which seeks to break the universe into its smallest components. But what if the universe doesn't lend itself to such dissection? What if reality is fundamentally emergent, arising from interactions and relationships rather than individual building blocks? This idea is gaining traction in fields like emergent spacetime, which suggests that space and time themselves might not be fundamental. Instead, they could emerge from more basic entities or principles, much like temperature emerges from the collective behavior of particles. If true, this would revolutionize our understanding of the cosmos, forcing us to rethink not only physics but also the nature of existence itself. The search for the theory of everything also raises profound philosophical questions. What does it mean to know something? Are we seeking a literal description of reality, or is our goal to create a model that makes predictions and offers insights? If the latter, does the theory of everything need to be true in an absolute sense, or merely useful? And if we ever find such a theory, would it truly mark the end of our quest for knowledge, or would it open new doors to deeper mysteries? There's also the question of our place in the universe. If the theory of everything reveals the ultimate laws of nature, what does that say about us? Are we insignificant specks in a vast, indifferent cosmos, or are we participants in a grand, interconnected system? Some interpretations of quantum mechanics suggest that observers play a fundamental role in shaping reality. If true, this implies that our search for the theory of everything is not just a scientific endeavor but a deeply personal one, tied to our identity as conscious beings. As we venture further into the unknown, it's clear that the journey itself is as important as the destination. The pursuit of the theory of everything is a testament to humanity's boundless curiosity and creativity. It's a reminder that even in the face of uncertainty, we continue to ask questions, push boundaries, and seek meaning. Whether or not we ever find the ultimate answer, the quest for understanding enriches our lives, connects us to the cosmos, and inspires us to dream of what might be possible. The implications of discovering the theory of everything extend far beyond science. Such a unifying principle would reshape not only how we understand the universe but also how we see ourselves within it. Imagine a world where the deepest mysteries of existence are laid bare, where we could explain the origins of matter, the nature of time, and even the fundamental cause of the universe itself. What would that mean for humanity's sense of purpose? Would it diminish the wonder of existence, or would it inspire us to new heights of creativity and exploration? To truly appreciate the gravity of this question, we must consider how each major scientific breakthrough has reshaped human thought. When Copernicus proposed that the Earth orbits the Sun, it upended our perception of the cosmos and our place in it. When Darwin introduced the theory of evolution, it challenged traditional notions of life and its origins. If the theory of everything were discovered, it would be the culmination of this progression, a singular insight that encapsulates all the workings of the universe. But could such a theory ever be complete? Some physicists argue that the universe is inherently complex, with layers of reality that may never be fully unraveled. Theoretical physicist John Archibald Wheeler famously said, "We are no longer satisfied with insights into particles, or fields of force, or geometry, or even space and time. Today we demand of physics some understanding of existence itself." This sentiment highlights the philosophical nature of the quest. Physics may uncover the rules of the game, but the why behind those rules might remain elusive. Consider, for example, the concept of symmetry, a cornerstone of modern physics. Symmetry describes situations where certain properties remain unchanged under specific transformations. It's a principle that governs everything from the shapes of molecules to the forces of nature. The equations of general relativity exhibit symmetries related to spacetime, while quantum mechanics relies on symmetries in particle interactions. Yet, symmetry is not absolute. It can be broken under certain conditions, giving rise to phenomena like mass and charge. Why does symmetry exist at all? And why does it sometimes break? These are questions that even the theory of everything might struggle to answer. Another challenge lies in the sheer diversity of phenomena that a unified theory must account for. From the delicate dance of subatomic particles to the violent collisions of galaxies, the universe operates on scales that seem impossibly vast and complex. Can a single set of equations truly capture all of this? Or will our understanding always be a patchwork of approximations, each valid only within a certain domain? There's also the question of free will. If the theory of everything describes the universe in its entirety, does it leave any room for human agency? Are we merely cogs in a cosmic machine, our actions predetermined by fundamental laws? Or does consciousness introduce an element of unpredictability that even the most comprehensive theory cannot account for? These questions tread the boundary between science and philosophy, reminding us that the search for knowledge often raises more questions than it answers. The search for the theory of everything also forces us to confront the limits of human cognition. Our brains evolved to navigate a middle-sized world of trees, rivers, and predators, not to comprehend the intricacies of quantum fields or the curvature of space-time. As we push the boundaries of understanding, we increasingly rely on abstract mathematics and advanced technologies to make sense of the universe. But what if some aspects of reality are simply beyond our capacity to grasp? Would that render the quest futile, or would it highlight the need for new ways of thinking? Some scientists argue that artificial intelligence could play a crucial role in overcoming these limitations. Advanced AI systems are already being used to analyze data, simulate complex phenomena, and even generate new hypotheses. In the future, AI might help us navigate the labyrinth of string theory or uncover hidden patterns in the fabric of spacetime. Yet, this raises another philosophical question. If an AI discovers the theory of everything, would we truly understand it, or would it remain an inscrutable black box of knowledge? As we ponder these questions, it's worth reflecting on the broader implications of a unifying theory. Such a discovery would have profound ethical and societal consequences, influencing fields as diverse as medicine, engineering, and environmental science. For instance, understanding the fundamental forces of nature could revolutionize energy production, enabling technologies that are cleaner, safer, and more efficient. It could also deepen our understanding of life itself, shedding light on the conditions that give rise to consciousness and the potential for life beyond Earth. At the same time, the theory of everything would challenge us to think more deeply about our responsibilities as stewards of the universe. If we hold the key to the cosmos, how should we use that knowledge? Would we harness it for the betterment of humanity, or would we risk repeating the mistakes of the past, using our understanding to exploit rather than protect? These are not merely hypothetical concerns but pressing questions that demand careful consideration. Ultimately, the search for the theory of everything is about more than physics. It's about the human spirit. It's about our unyielding desire to explore, to understand, and to find our place in the cosmos. Whether or not we succeed in this quest, the journey itself is a testament to the power of curiosity and imagination. It's a reminder that even in the face of uncertainty, we continue to ask the big questions, striving to make sense of a universe that is both mysterious and profoundly beautiful. And perhaps that's the greatest mystery of all, why the universe is comprehensible at all, why it follows laws and patterns that we can discern. In seeking the theory of everything, we are not just trying to solve a puzzle, we are engaging with the deepest aspects of existence, reaching for the stars in every sense of the phrase. This profound journey into understanding the universe continues to provoke some of the most fundamental questions of existence. Why does the universe seem so perfectly tuned for life? Why do the laws of nature allow for the emergence of complexity, from galaxies and stars to life and consciousness? The theory of everything, if ever discovered, would not only unify physics but might also illuminate answers to such profound mysteries. One of the key concepts in this search is the anthropic principle, which suggests that the laws of the universe appear fine-tuned because, if they were not, we would not be here to observe them. For example, the strength of the gravitational force, the charge of the electron, and the expansion rate of the universe are all precisely set within ranges that allow stars, planets, and life to exist. But is this fine-tuning a product of design, a consequence of deeper laws, or simply a result of chance? The anthropic principle intersects intriguingly with the concept of the multiverse, the idea that our universe is just one of an infinite number of universes, each with its own set of physical laws. If the multiverse exists, it might provide a statistical explanation for fine-tuning. We live in a universe that allows for life because there are countless others that do not. While this idea shifts the focus away from the unique properties of our universe, it also raises new questions. For instance, how could we ever confirm the existence of other universes? And if they are fundamentally disconnected from our own, what would that mean for our understanding of reality? The multiverse theory is closely tied to string theory, which, as previously discussed, suggests that the universe consists of tiny vibrating strings. These strings operate in a multidimensional framework, with most dimensions curled up so tightly that they are imperceptible. String theory predicts the existence of a vast landscape of possible universes, each corresponding to a different configuration of these hidden dimensions. This landscape provides a theoretical basis for the multiverse, though the challenge of testing such predictions remains daunting. Beyond string theory, other approaches to the theory of everything grapple with equally profound questions. Loop quantum gravity, for instance, offers a different vision of space-time. In this framework, space-time is not a smooth continuum but is instead composed of tiny, discrete units, like the pixels on a screen. These, quantum loops, provide a way to unify gravity with quantum mechanics without requiring extra dimensions. Loop quantum gravity suggests that space and time themselves might emerge from a more fundamental level of reality, challenging our most basic assumptions about existence. These competing theories highlight an important aspect of the quest for the theory of everything, the need for experimental evidence. While mathematics can guide theoretical developments, science ultimately relies on observations to confirm or refute hypotheses. For now, much of the evidence needed to test these theories lies beyond our current technological capabilities. Detecting quantum gravity effects, probing higher dimensions, or observing multiverse phenomena may require breakthroughs in both theory and engineering. Interestingly, some researchers suggest that clues to the theory of everything might already be hidden in plain sight, encoded in the patterns of the cosmic microwave background radiation, or the behavior of neutrinos. Others propose using particle accelerators to reach energies high enough to glimpse the underlying structure of reality. These ambitious projects represent the cutting edge of physics, driven by the hope that even the smallest hint could unlock a new era of discovery. The search also forces us to reconsider the nature of time. In classical physics, time is a linear progression, a steady march from past to future. But in the realm of quantum mechanics, time becomes a more fluid concept, potentially reversible, or even non-existent at the smallest scales. General relativity complicates this picture further, showing how time can bend, stretch, or slow down in the presence of massive objects. A unified theory would need to reconcile these differing views, providing a coherent explanation for one of the most fundamental aspects of our experience. Yet, as we probe deeper, we encounter the possibility that some aspects of the universe might be inherently unknowable. The Heisenberg uncertainty principle, for example, places limits on how precisely we can measure certain properties of particles. This intrinsic uncertainty could extend to other areas of physics, suggesting that the universe may always retain an element of mystery. If this is true, the theory of everything might not be a final answer but a framework that acknowledges and accommodates uncertainty. Philosophers have long grappled with the implications of such limitations. Is the human desire for ultimate knowledge a reflection of reality, or merely a product of our curiosity? Could the search for the theory of everything be more about the journey than the destination? These questions remind us that science is not just a method for acquiring knowledge, but a profound expression of the human spirit. As we move forward, the interplay between science and philosophy becomes increasingly important. Questions about the nature of reality, the origins of the universe, and the role of consciousness blur the boundaries between disciplines. While physicists build mathematical models, philosophers explore the implications of those models for our understanding of existence. Together, they form a dialogue that enriches our quest for meaning and truth. This brings us to one of the most intriguing aspects of the search, the role of consciousness. Some theories suggest that consciousness is not merely a byproduct of physical processes, but a fundamental aspect of the universe. If true, this would have profound implications for the theory of everything, requiring us to integrate not only the forces of nature but also the phenomenon of awareness. Could consciousness itself hold the key to understanding the cosmos? Or is it an emergent property that arises only under specific conditions? These questions invite us to think deeply about the relationship between the observer and the observed. In quantum mechanics, the act of measurement plays a crucial role in determining outcomes. This observer effect raises profound questions about the role of human perception in shaping reality. If the universe depends in some way on our observation, what does that mean for its fundamental nature? Could the theory of everything ultimately reveal a universe that is inseparable from the act of observing it? As we ponder these mysteries, it becomes clear that the search for the theory of everything is as much a philosophical quest as a scientific one. It challenges us to confront the deepest questions of existence, to explore the boundaries of knowledge, and to imagine new possibilities. Whether or not we ever achieve a final answer, the journey itself is a testament to the power of human curiosity and imagination. The journey toward understanding the universe through a unified theory of everything continues to inspire generations of scientists, philosophers, and curious minds alike. At its core, this pursuit reflects humanity's unyielding desire to uncover the ultimate truths of existence, even if those truths challenge our current paradigms of thought. As we delve deeper into this exploration, it's essential to address the broader implications of such a theory and the intricate connections it may reveal about our place in the cosmos. One of the most tantalizing aspects of the theory of everything lies in its potential to redefine the relationship between the physical and the metaphysical. Historically, science and philosophy have often been seen as separate domains, yet the questions posed by modern physics blur the boundaries between them. For instance, if time and space are emergent properties rather than fundamental realities, what does this mean for concepts like causality, free will, and even the nature of existence itself? Could the universe's structure be more akin to an elaborate simulation or a holographic projection, as some theories suggest? The holographic principle is a compelling idea that stems from string theory and black hole thermodynamics. It posits that the information contained within a three-dimensional volume of space can be encoded on a two-dimensional surface surrounding it. This principle was initially proposed to solve paradoxes related to black holes and entropy but has since gained traction as a possible framework for describing the entire universe. If true, it would imply that our perception of reality as a three-dimensional space is, in some sense, an illusion. The implications of this are profound. Everything we experience as physical reality might be a projection of more fundamental, lower-dimensional processes. Such ideas challenge our intuition and require us to reconsider the very fabric of reality. For centuries, humanity has relied on sensory experiences to understand the world, but the pursuit of a unified theory forces us to go beyond what is immediately observable. In doing so, we must confront the limits of human cognition. Our brains, shaped by millions of years of evolution, are optimized for survival in a world of macroscopic objects and relatively slow processes. The quantum and cosmological scales, however, operate in realms far removed from our everyday experiences, demanding abstract thinking and mathematical formalism to bridge the gap. The role of mathematics in this quest cannot be overstated. Mathematics is often described as the language of the universe, an elegant and precise tool for describing the laws of nature. But why does mathematics work so well? Is it a human invention, or does it reflect an intrinsic order within the cosmos? This question is deeply intertwined with the search for the theory of everything. A unified theory would likely be expressed through mathematical equations that encapsulate the fundamental principles governing all of existence. Yet, as we build increasingly sophisticated models, we must also grapple with the possibility that mathematics itself may have limits in describing reality. This brings us to the concept of emergence, the idea that complex systems and phenomena arise from the interactions of simpler components. Emergence is a cornerstone of many scientific fields, from biology to sociology, and it may also play a critical role in physics. For example, while the behavior of individual particles is governed by quantum mechanics, the macroscopic world we experience emerges from the collective behavior of countless particles. Similarly, time and space might emerge from deeper, more fundamental processes described by a unified theory. If emergence is a universal principle, it could provide a bridge between the quantum and cosmological scales, helping to reconcile their seemingly disparate laws. Emergence also has philosophical implications, particularly in the context of reductionism, the idea that everything can be understood by breaking it down into its smallest components. While reductionism has been a powerful tool in science, the concept of emergence suggests that some phenomena cannot be fully explained by their parts alone. Instead, new properties and behaviors arise at higher levels of complexity, requiring us to consider the system as a whole. This perspective aligns with holistic approaches in philosophy and suggests that the theory of everything may need to account for both the microcosm and the macrocosm in an integrated framework. This iterative nature of discovery is evident in the interplay between theory and experiment. While theoretical physics provides the framework for understanding the universe, experimental physics offers the tools to test and refine those ideas. Consider the role of particle accelerators like the Large Hadron Collider, LHC. By smashing particles together at high energies, the LHC allows scientists to probe the fundamental building blocks of matter and search for evidence of new phenomena. The discovery of the Higgs boson in 2012 was a landmark achievement, confirming a key prediction of the Standard Model. Yet, the LHC has also highlighted the gaps in our understanding, such as the absence of evidence for supersymmetry or extra dimensions. These gaps point to the limitations of our current experimental capabilities. To explore the next frontier, scientists are proposing even more ambitious projects, such as the Future Circular Collider or space-based observatories capable of detecting quantum gravitational waves. These initiatives represent the cutting edge of human ingenuity, requiring international collaboration and significant resources. Yet, they also underscore the importance of patience and persistence in the search for a unified theory. The answers we seek may not come in our lifetimes, but each step forward brings us closer to the truth. As we contemplate the future of this journey, it's important to remember that the theory of everything is not just a scientific pursuit, it's a deeply human endeavor. It reflects our innate curiosity, our desire to understand our origins, and our quest for meaning in a vast and mysterious universe. Whether or not we ever achieve a final answer, the pursuit itself is a testament to the resilience and creativity of the human spirit. It reminds us that the greatest mysteries are not obstacles to be overcome but invitations to explore, to wonder, and to dream. The theory of everything (TOE) is not only about solving the fundamental puzzles of physics, it's about finding a deeper understanding of existence itself. As we continue to search for the ultimate framework, we are constantly reminded that there is much we still don't know. This pursuit pushes us to ask bigger questions, even beyond the realm of science itself. What is the true nature of reality? What does it mean to exist, to experience, to perceive? The answers to these questions are not only in equations and experiments, but also in our ability to stretch the limits of our imagination, creativity, and critical thinking. While the search for a unified theory has brought us closer to understanding the cosmos, it has also exposed how little we truly understand about the nature of space, time, and energy. To bring together quantum mechanics and general relativity into one cohesive theory, scientists are exploring groundbreaking ideas that challenge our very concepts of the universe. The deeper we go, the more we realize how fragile our current understanding is, and how much more there is to uncover. A fascinating development in this quest is the rise of multiverse theory. While string theory and loop quantum gravity focus on unifying the forces of nature within our universe, the multiverse theory suggests that our universe may be just one of an infinite number of parallel universes, each with different physical laws, constants, and properties. This theory has been met with both excitement and skepticism, as it opens up incredible possibilities about the nature of reality. If true, it would revolutionize our understanding of the cosmos and our place within it. It raises the possibility that there are countless worlds beyond our own, each with its own unique set of physical conditions, and each possibly governed by entirely different laws of nature. The concept of the multiverse may sound far-fetched, but it's grounded in serious scientific speculation. One of the key motivations for multiverse theories is the fine-tuning problem in cosmology. Our universe seems to be exquisitely fine-tuned for life, with the fundamental constants, such as the strength of gravity, the charge of the electron, and the cosmological constant, falling within extremely narrow ranges that allow for the existence of complex structures like galaxies, stars, and life itself. The chances of these constants randomly falling into such a precise arrangement seem incredibly small, leading some scientists to propose the idea of a multiverse, an ensemble of universes where each one has different constants and properties, and we just happen to live in the one that supports life. However, while multiverse theories offer intriguing possibilities, they also face significant challenges. One of the most pressing issues is the lack of empirical evidence. As of now, there is no direct way to test the existence of other universes, which leaves the multiverse theory in a realm of speculation rather than concrete science. The inability to test or observe other universes has made some physicists question whether the theory is truly scientific or if it's merely an elegant but untestable hypothesis. Despite the challenges, the multiverse theory has found support among certain physicists, including those working on string theory and cosmology. The idea of a multiverse fits naturally with the landscape of string theory, where there are multiple possible configurations of extra dimensions that can give rise to different physical laws in different universes. In fact, string theory predicts a vast landscape of potential universes, each with its own set of fundamental constants and particles. This opens up the possibility that our universe is just one of many, each with its own unique structure and properties. As we explore these ideas, it becomes increasingly clear that the search for a theory of everything is not just about finding a single, unified equation. It's about reshaping our understanding of reality itself, transforming the way we think about space, time, matter, and energy. Whether or not we achieve a complete theory of everything, the journey will continue to push the boundaries of our knowledge, revealing new realms of possibility, and inviting us to think in ways we never have before. String theory, loop quantum gravity, and the multiverse are only the beginning of what may be an even more profound revelation waiting at the end of this long scientific odyssey. Perhaps, As we continue to delve deeper into the mysteries of the universe, we will uncover new principles that transcend our current models. These principles could have profound implications for technology, philosophy, and even our understanding of consciousness itself. For instance, if space-time is emergent, this might mean that the universe could be understood as a vast, interconnected network, where every particle and event is related to every other particle and event in ways that we can scarcely imagine. One area that has garnered increasing attention in recent years is the concept of quantum gravity, the quest to understand how gravity behaves on the smallest, quantum scale. This is one of the major open questions in modern physics. While general relativity describes the force of gravity at large scales, from planets to galaxies, it doesn't account for quantum mechanics, which governs the behavior of subatomic particles. Quantum gravity seeks to reconcile these two descriptions by providing a theory that works on both the quantum scale and the cosmological scale. This could lead to profound discoveries, such as understanding the nature of black holes or the mechanics of the Big Bang. One of the leading contenders in the field of quantum gravity is loop quantum gravity, LQG, a theory that seeks to describe spacetime itself as a network of discrete, quantized units, rather than as a smooth, continuous fabric. In LQG, spacetime is made up of tiny loops of energy, which combine to form the structure of the universe. This theory challenges our intuitive understanding of space and time and suggests that, at the most fundamental level, the universe is composed of discrete chunks of spacetime rather than a smooth continuum. If correct, this would drastically change our understanding of gravity, space, and time. But loop quantum gravity isn't the only theory in the race to solve the mysteries of quantum gravity. String theory remains one of the most promising approaches, offering the tantalizing possibility of unifying all of the fundamental forces of nature into a single framework. As we've seen earlier, string theory proposes that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings, vibrating at different frequencies. These vibrations give rise to the different particles and forces we observe in nature. String theory also requires the existence of extra-spatial dimensions, beyond the familiar 3 dimensions of space and 1 dimension of time, giving rise to the possibility of parallel universes or alternate realities. While both string theory and loop quantum gravity offer exciting possibilities, either theory has been conclusively proven, and each faces significant challenges. The quest for a unified theory of everything remains one of the most profound and elusive goals in science. The pursuit is not just about answering specific questions or solving isolated problems. It's about uncovering the fundamental truths of existence, the very nature of reality itself. As we continue this search, we must acknowledge that the theory of everything is not just an equation we hope to find. It's a new way of perceiving the universe, a new lens through which we can interpret the complex phenomena around us. Our understanding of the laws that govern reality has evolved over time, but the biggest hurdle lies in bridging the divide between the quantum world of particles and the macroscopic world that we experience daily. To see why this quest is so complex, let's explore some of the deeper aspects of quantum mechanics and general relativity. Quantum mechanics deals with the behavior of the smallest particles in the universe, like electrons, protons, and quarks. At this level, particles don't follow the predictable paths we associate with classical mechanics. Instead, they exhibit strange and unpredictable behavior that defies our conventional understanding of the world. These particles can exist in multiple states simultaneously, and their properties, such as position and momentum, are not fixed until they are observed. The theory relies heavily on probability rather than certainty. In contrast, general relativity describes the large-scale structure of the universe. It deals with the fabric of spacetime itself and the effects of gravity on it. According to Einstein's theory, massive objects like planets and stars warp the spacetime around them, and this curvature determines how objects move through space. This framework successfully explains the behavior of planets, black holes, and even the expansion of the universe. However, it doesn't provide a framework for understanding how gravity works at the quantum level. And therein lies the rub. Gravity behaves differently in the quantum world, and quantum mechanics doesn't handle gravity. For over a century, these two theories, quantum mechanics and general relativity, have remained largely separate. Physicists have tried to merge them, but despite numerous efforts, no theory has yet successfully unified them into a single framework. The quest for the theory of everything is about finding that elusive theory that would describe all forces and particles within one comprehensive framework. But even as we focus on the quest to unify quantum mechanics with general relativity, there are other groundbreaking ideas pushing us toward new frontiers. One such idea is the possibility that space-time itself is not continuous, but rather quantized. In other words, the very fabric of space-time might be made up of discrete chunks, and our perception of a smooth and continuous universe might be an illusion. This idea has been explored in various approaches to quantum gravity, including loop quantum gravity. In loop quantum gravity, space-time is thought to consist of tiny loops of quantum energy, which are not continuous but rather discrete. These loops form a network that underlies the entire universe, providing the structure for both matter and space-time itself. This contrasts with the smooth, continuous fabric described by general relativity. If space-time is fundamentally granular, then the idea of a theory of everything must be capable of incorporating this discrete structure of space-time. On the other hand, string theory also attempts to address these challenges but takes a radically different approach. Instead of considering space-time as a backdrop upon which particles interact, string theory proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings exist in higher dimensions, up to 11 in some versions of the theory, and their vibrations give rise to the particles we observe in nature. This idea naturally brings together the forces of gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, suggesting that they are different manifestations of the same underlying entity. String theory has a number of appealing features. For one, it provides a framework that could unify all the forces of nature, including gravity, into a single theory. Moreover, string theory is consistent with the principles of quantum mechanics, allowing it to describe phenomena at both the microscopic and macroscopic levels. However, string theory is still in its infancy, and much work remains to be done before it can be tested experimentally. The key challenge lies in the fact that string theory predicts the existence of extra-spatial dimensions beyond the familiar 3 of space and 1 of time, and these extra dimensions are far too small to detect with current technology. Despite these challenges, the promise of string theory has captured the imaginations of many scientists. It offers the potential to answer some of the biggest questions in physics, such as why the fundamental constants of nature are what they are and whether there are multiple universes. Yet, without concrete experimental evidence, string theory remains a speculative idea, one that continues to generate debate and intrigue among physicists. Another interesting aspect of this quest for a unified theory is the growing intersection between cosmology and quantum mechanics. Historically, these fields were seen as distinct, with cosmology focusing on the large-scale structure of the universe and quantum mechanics dealing with the minuscule particles that make up everything we see. However, as our understanding of the universe has advanced, we've realized that the two are inextricably linked. The physics of the very small, quantum mechanics, and the very large, cosmology, must be part of the same overarching theory. Consider, for example, the study of black holes, regions of space where gravity is so strong that not even light can escape. Black holes are governed by both general relativity, the theory of gravity, and quantum mechanics, but reconciling these two theories in the context of black holes is incredibly difficult. One of the biggest mysteries surrounding black holes is the so-called information paradox. According to quantum mechanics, information cannot be lost, but when matter falls into a black hole, it appears to be lost forever. This paradox is one of the most pressing questions in theoretical physics and highlights the need for a unified theory that can address both the quantum and relativistic aspects of reality. The development of a theory of everything would also have profound implications for the way we understand the origin of the universe. The Big Bang theory suggests that the universe began as a singularity, an infinitely dense point where the laws of physics, as we understand them, break down. At this point, space-time itself was condensed into a tiny, hot, and dense state. A unified theory could help us understand what happened in the moments leading up to the Big Bang, and how the universe has evolved since. It could also offer insights into the true nature of dark matter and dark energy, which make up the vast majority of the universe's mass energy content but remain largely mysterious. Moreover, a theory of everything could also shed light on the possibility of parallel universes or other dimensions. String theory and related ideas suggest that our universe may be part of a multiverse, a collection of universes that could have different physical laws and constants. Some of these universes may be completely different from our own, with entirely different properties and even different forms of life. The existence of such parallel universes raises profound questions about the nature of reality and our place in the cosmos. But for all its promise, the search for the theory of everything is not without its criticisms. Some physicists argue that the theory may be fundamentally unattainable, that the universe may be too complex and the limits of human understanding too constrained to ever achieve a complete, unified theory. Others point out that the theory of everything may not necessarily answer all the philosophical or metaphysical questions about existence, meaning, and consciousness. In fact, it's possible that the deeper mysteries of the universe are not even scientific in nature but belong to other realms of human inquiry, such as philosophy, theology, or even art. Still, the search for a theory of everything represents one of the most profound and ambitious intellectual endeavors ever undertaken by humanity. It is not just about understanding how the universe works, it's about discovering our place within it and uncovering the ultimate truths that lie behind all of existence. As we continue our exploration, the theory of everything remains a shining beacon at the horizon of human knowledge, a tantalizing vision that may one day change the way we see ourselves and the universe we inhabit. The search for a theory of everything (TOE) also pushes the boundaries of mathematics and theoretical physics. In many ways, it can be seen as a grand puzzle, where the pieces are scattered across different areas of research. To make progress, scientists must use new mathematical tools, construct new frameworks, and develop entirely novel ideas. However, one of the major challenges is that the current experimental techniques are not equipped to test some of the predictions made by the leading theories, such as string theory or loop quantum gravity. These theories often deal with energies or scales that are far beyond what we can reach with present-day technology. Take, for example, the idea of extra dimensions in string theory. The theory suggests that our universe may have more than the familiar 3 spatial dimensions and 1 time dimension. These extra dimensions could be compactified, meaning they are folded up into a very small space, invisible to us. If this is true, it could revolutionize the way we understand space and time. Yet, how do we test this idea? It's incredibly difficult, because these extra dimensions are thought to be on the Planck scale, which is far smaller than we can currently measure. Similarly, loop quantum gravity presents its own challenges. The theory posits that space-time itself is quantized and made up of discrete units. However, these units, or quantum loops, are incredibly small, much smaller than an atom. The problem is that our current tools, such as particle accelerators, are unable to detect these incredibly small phenomena directly. Until we develop new methods or technologies, our ability to test these theories will remain limited, and we may only be able to explore their validity indirectly, through indirect evidence or computational simulations. Despite these hurdles, scientists continue to develop creative ways to probe the validity of these theories. One promising avenue is cosmology, specifically, the study of the early universe. The moments just after the Big Bang are thought to hold critical clues about the nature of reality and the potential unification of forces. By studying the cosmic microwave background radiation, CMB, which is the afterglow of the Big Bang, researchers can learn about the conditions of the universe in its infancy. Tiny fluctuations in the CMB provide a snapshot of the universe's early state, offering hints about the fundamental forces and particles that existed at the time. Researchers also look to black holes as natural laboratories for testing theories of gravity, quantum mechanics, and the theory of everything. The extreme environments around black holes, particularly the event horizon, where gravity is so strong that not even light can escape, provide an opportunity to study physics under extreme conditions. The study of Hawking radiation, for example, which is the theoretical radiation emitted by black holes due to quantum effects near the event horizon, may hold important clues about the relationship between quantum mechanics and gravity. One of the most tantalizing areas of research today is the study of quantum entanglement and its connection to the fabric of reality itself. Quantum entanglement describes a phenomenon in which two particles become connected in such a way that the state of one particle is instantly linked to the state of another, regardless of the distance between them. This spooky action at a distance seems to defy the principles of locality that govern classical physics. However, it also suggests that the universe may be more interconnected than we currently understand, and that the separation between objects and events may be an illusion at some fundamental level. Recent experiments have demonstrated that quantum entanglement can be observed on scales much larger than previously thought. This opens up the possibility that the entangled nature of particles could play a key role in the way the universe is organized at its most basic level. If entanglement is indeed fundamental to the structure of spacetime, it could help to bridge the gap between quantum mechanics and general relativity. As scientists continue to delve into these mysteries, they are confronted with the growing realization that the theory of everything may not be just a single equation or framework, but a multifaceted and deeply interconnected understanding of reality. It could involve a combination of string theory, loop quantum gravity, and other novel approaches, each contributing its own piece to the puzzle. It may even require a completely new conceptual leap that we cannot yet imagine. And even if a theory of everything is eventually discovered, there's still the possibility that it will raise as many questions as it answers. The theory might provide a unified description of the forces and particles that govern the universe, but it may not answer the deeper philosophical questions about the nature of consciousness, free will, or the meaning of existence. After all, even if we could describe every aspect of the physical universe, we might still be left with a profound mystery about the why of it all. Why does the universe exist in the way that it does? Why are the fundamental constants of nature what they are? And why are we here to ask these questions? This is where the search for the theory of everything takes on a more metaphysical dimension. As we delve deeper into the nature of reality, we are not only uncovering the secrets of the universe, but we are also confronting the limits of human knowledge and understanding. The pursuit of this ultimate theory challenges us to confront the very nature of existence and our place in the cosmos. It asks us to reconsider our assumptions about the world, to question the boundaries between science and philosophy, and to reflect on the deeper mysteries that may lie beyond the reach of scientific inquiry. As much as science strives to provide answers, it's clear that the theory of everything is as much about the journey as it is about the destination. Each new discovery, each new breakthrough, brings us one step closer to understanding the universe, but it also opens up new avenues for exploration and new mysteries to ponder. Perhaps, in the end, the search for the theory of everything is not just about finding a single unified equation, but about embracing the infinite complexity of the universe and the infinite possibilities for discovery that lie ahead. The road to the theory of everything is long and uncertain, but it is also filled with wonder, discovery, and the excitement of exploring the deepest truths of existence. Whether or not we ever reach the ultimate theory, the journey itself will undoubtedly transform our understanding of the universe and our place within it. The search for the theory of everything is one of humanity's greatest intellectual pursuits, a pursuit that not only seeks to explain the fundamental forces of nature but also challenges us to rethink the very nature of reality itself. With each new insight, we inch closer to the realization that the universe is far more mysterious and interconnected than we could have ever imagined. But the questions that arise from this search may be just as important as the answers themselves, as they force us to reflect on the nature of existence and the ultimate purpose of the universe. The story of our quest for understanding is far from over, and who knows where this search will take us in the future. We may one day discover the unifying theory that brings all of physics together, or we may come to understand that the universe is simply too complex for a single theory to ever encapsulate. Whatever the outcome, the pursuit of knowledge and the desire to answer the greatest questions of existence will continue to drive humanity forward, ever searching for the truth, ever curious, and always questioning the very nature of reality. As the search for a theory of everything continues, there are other theoretical approaches that may hold potential answers to the ultimate nature of the universe. Concepts that stretch the boundaries of imagination and challenge our current understanding of space, time, and the very fabric of reality. One such approach that has been gaining traction in recent years is holographic theory, particularly the holographic principle, which proposes that the entire universe could be a projection of information encoded on a distant boundary, much like a hologram. This idea stems from the study of black holes, where certain properties of black holes, like entropy, seem to suggest that information about the matter that falls into them could be encoded at the event horizon rather than inside the black hole itself. This principle has the potential to revolutionize our understanding of space-time, and could lead to a new theory that unifies quantum mechanics and gravity. This holographic view challenges the idea of space-time as a fundamental entity, and instead suggests that it could be an emergent property arising from more fundamental processes. If this theory holds up, it could open up entirely new ways of thinking about reality, where everything we experience as real is actually a projection from a distant, lower-dimensional surface. This concept echoes the findings of string theory and loop quantum gravity, both of which are working towards similar ends, trying to explain the universe at its most fundamental level. In this evolving landscape, some scientists believe that the theory of everything might not even look like the neatly packaged equations that we've grown accustomed to. Instead, it might be more akin to a framework that offers a coherent set of principles, laws, or rules that govern the entire universe. It could include aspects of different theories, with each piece of the puzzle revealing a different aspect of reality, just as the different forces of nature, gravitational, electromagnetic, weak, and strong, are described by distinct laws in current physics. The unification, then, might not come from discovering a single formula but through the realization that these various approaches are part of the same grand tapestry. But where do we go from here? For the theory of everything to become a reality, we will need to not only develop new theories but also create the tools and methodologies to test these theories. One such advancement in experimental physics is the growing field of quantum computing. Quantum computers, which exploit the strange properties of quantum mechanics to perform calculations at speeds far beyond the capabilities of classical computers, may offer a way to simulate the behaviors of quantum fields, particles, and the interactions of forces on a scale previously thought impossible. With enough computing power, it might be possible to simulate universes, test quantum models, and even explore different versions of string theory in ways that were previously beyond our reach. Yet, as promising as quantum computing is, it is still in its infancy. To fully unlock its potential, researchers must overcome numerous technical hurdles, from the challenges of maintaining quantum coherence to the ability to scale quantum systems. Still, the progress that has been made in this field is astounding, and as quantum computers become more powerful, they could open up new paths towards solving the most pressing questions in fundamental physics. Some physicists even suggest that quantum computers could ultimately help us discover a theory of everything by running simulations of the universe at the most fundamental level, enabling us to see how the various forces interact in different configurations. Moreover, the Large Hadron Collider, LHC, the world's most powerful particle accelerator, continues to be an invaluable tool in the search for a deeper understanding of the universe. The LHC, located at CERN, has already made groundbreaking discoveries, including the confirmation of the Higgs boson particle in 2012, which confirmed the existence of the Higgs field and solidified our understanding of mass. However, scientists believe that there is much more to uncover. As the LHC continues to explore higher energy scales, it could provide critical insights into the behavior of matter at the most extreme conditions, potentially uncovering new particles or forces that could point toward a unified theory of physics. There is a possibility that new phenomena will emerge from these experiments, phenomena that we cannot even imagine right now, that could challenge existing paradigms and bring us closer to a unified theory. In addition to the LHC, space-based experiments may also play a key role in the search for the theory of everything. For instance, gravitational wave astronomy has already yielded incredible insights into the nature of space-time. The detection of gravitational waves from distant black hole mergers by the LIGO Observatory has opened a new window into the universe, allowing scientists to observe the most violent events in the cosmos. These waves carry crucial information about the nature of gravity, the structure of space-time, and the very fabric of the universe itself. As gravitational wave detectors become more sensitive, they may uncover new phenomena that could shed light on the unification of quantum mechanics and general relativity. Similarly, the study of cosmic inflation, the rapid expansion of the universe in the first moments after the Big Bang, could offer valuable clues about the unification of forces. Inflationary models predict that the universe underwent an incredibly fast expansion, smoothing out any initial irregularities and leading to the large-scale structure we observe today. Understanding the details of this process could provide deep insights into the origins of the universe and the fundamental forces that governed its creation. But even with all of these advancements, the search for a theory of everything is not just a scientific endeavor, it is a deeply philosophical one. As we inch closer to uncovering the underlying principles of the universe, we are forced to confront deeper questions about the nature of reality itself. Is the universe ultimately deterministic, governed by strict laws of cause and effect, or is it random and unpredictable, shaped by quantum fluctuations? Do we live in a universe that is fundamentally connected, or is our perception of interconnectedness merely an illusion? And what does it mean for us as humans, with our limited perspective, to strive for a unified understanding of a universe that is so vast, complex, and potentially beyond our comprehension? The search for the theory of everything is both an intellectual and existential pursuit. As we attempt to understand the fundamental laws that govern everything, we are also confronting our own place within the cosmos. The ultimate theory might give us the answers we seek, but it may also reveal that some questions are simply too vast for the human mind to grasp. And yet, it is this very uncertainty that drives us forward. For it is through the pursuit of knowledge and understanding, through the desire to make sense of the universe, that we find meaning and purpose. Ultimately, the search for the theory of everything is not just about answering the big questions, it's about the process itself. It's about pushing the boundaries of human knowledge, challenging the assumptions we've held for centuries, and embracing the mystery of existence. Even if we never find the final answer, the journey of discovery itself is one of the most profound and exciting endeavors humanity has ever undertaken. The theory of everything may be more than just a theory. It may be a reflection of our own endless curiosity, our desire to understand the cosmos, and our quest for meaning in an ever-expanding universe. Whether or not we reach the ultimate theory, the search itself will continue to inspire generations of scientists, philosophers, and dreamers alike, pushing us to ask bigger questions, seek deeper truths, and strive for an understanding of the universe that transcends the limits of our imagination. As we continue to venture deeper into the search for a theory of everything, it's essential to recognize that we are not only unraveling the mysteries of the universe but also reshaping the very foundation of physics. Theories like string theory, loop quantum gravity, and the holographic principle are not merely abstract concepts. They represent new paradigms that challenge our understanding of space, time, and reality itself. Each theory introduces radical ideas that could redefine the very nature of existence, but we have yet to prove which, if any, hold the keys to unlocking a unified theory of everything. In string theory, for example, we find the suggestion that all particles and forces are manifestations of tiny, vibrating strings. These strings are hypothesized to exist in more than the familiar 3 dimensions of space and 1 dimension of time. String theory posits the existence of up to 11 dimensions, in its most popular version, M theory, with additional dimensions being curled up and hidden from our perception. If proven true, this would mean that the universe we see around us is only a fraction of a much larger, more complex reality, where particles interact through extra-dimensional spaces we cannot yet directly observe. This opens up the possibility that phenomena we currently cannot explain, such as the force of gravity or the nature of dark matter, could find their origins in these extra dimensions. However, while string theory presents an elegant framework that ties together quantum mechanics and general relativity, it is still very much a work in progress. The lack of experimental evidence has raised skepticism among some physicists, who are wary of theories that cannot be tested or falsified. String theory's elegance, in fact, lies in its complexity and ability to explain multiple phenomena, but without concrete evidence, it remains in the realm of the hypothetical. Loop quantum gravity, LQG, on the other hand, takes a different approach to the unification of quantum mechanics and general relativity. LQG seeks to describe gravity in quantum mechanical terms, suggesting that spacetime itself is made up of tiny, discrete loops or quantum chunks. These loops of spacetime are linked together, creating a sort of fabric that could explain how the gravitational force works on a microscopic scale. LQG also offers a resolution to the problem of singularities, such as those found at the center of black holes, where the curvature of spacetime becomes infinite. Instead of singularities, LQG proposes that spacetime becomes finite and behaves in a quantum fashion at very small scales, potentially offering a way to avoid the infinite density of a black hole singularity. The beauty of LQG is that it is based on solid, testable principles, offering a quantum theory of gravity without requiring the existence of extra dimensions or the complex, abstract mathematics of string theory. However, much like string theory, LQG also faces its own challenges in terms of experimental verification. The scales at which quantum gravitational effects become noticeable are so small that we currently lack the technology to observe them directly. However, some scientists remain hopeful that advances in high-energy physics or quantum computing might one day provide the means to test these ideas. On a broader scale, one of the most exciting ideas in the search for a unified theory comes from the holographic principle, a concept that emerged from the study of black holes and has since found connections to quantum gravity. The holographic principle suggests that the entire universe could be described by information stored on a two-dimensional surface, much like how a hologram encodes three-dimensional images on a flat surface. In this view, our three-dimensional reality, including space and time, might actually be a projection of more fundamental two-dimensional information. The holographic principle came into focus when scientists studied the entropy of black holes, the measure of how much information is contained within them. They discovered that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume, which suggests that the information contained within a black hole might be encoded on its surface rather than in its interior. This realization led to the idea that the entire universe could be described by such surface-bound information. If this idea is correct, the universe would essentially be a massive, complex hologram, a projection of data that exists in a lower-dimensional space. This might sound mind-boggling, but the holographic principle offers a fascinating way to think about space and time. It provides a potential solution to some of the deepest puzzles in physics, including how to reconcile quantum mechanics and gravity. But much like other theories in the search for a theory of everything, the holographic principle is still largely speculative. Theoretical physicists are continuing to explore its implications, and while there is no direct experimental evidence yet, the idea continues to gain attention for its potential to unify the various forces of nature into a single, coherent theory. Beyond these major theories, there is another exciting frontier in the search for a theory of everything that draws upon our understanding of information theory. Information is at the core of modern physics, and the way in which it behaves in extreme conditions may hold crucial insights into the workings of the universe. Quantum information theory deals with how quantum systems encode, store, and transmit information, and has become an essential tool in the study of quantum mechanics and quantum computing. The study of quantum information is leading some physicists to propose that the ultimate laws of physics might be fundamentally information-based, meaning that the universe itself could be a massive computation. This idea is closely linked to the holographic principle and string theory, suggesting that the very fabric of spacetime could arise from fundamental bits of information. Information-based approaches to understanding the universe are still in their early stages, but they represent a promising direction for future research. If the universe operates like a gigantic computer, governed by rules of computation and information processing, then the theory of everything might not be a set of mathematical equations describing particles and forces, but rather an understanding of the fundamental code that underlies everything in existence. As we look ahead, it's clear that the search for the theory of everything is not just a matter of finding a single, final theory. It is about exploring new avenues of thought, developing innovative tools for discovery, and pushing the boundaries of what we know. In this quest, physicists are working to break down the walls between the major forces of nature, explore the deeper structure of space and time, and make sense of the strange, paradoxical behaviors that arise when quantum mechanics and gravity collide. The search is not just about physics, it is a journey into the very nature of reality. It is about pushing human understanding to its limits, challenging the way we think about the universe and our place within it. Whether we ultimately discover a theory of everything or whether the quest itself reveals more questions than answers, the journey will undoubtedly continue to inspire, captivate, and challenge the minds of those who dare to look deeper into the mysteries of the cosmos. In the grandest sense, the theory of everything may not just be a scientific goal, but a metaphor for the human spirit, a reflection of our ceaseless curiosity, our drive to understand the unknown, and our ability to imagine a reality that goes far beyond the limits of our senses. The search will continue, and with each discovery, we will inch closer to the answer to one of humanity's most profound questions: what is the true nature of the universe, and what laws govern everything within it? As we dive further into this intricate search, it's important to recognize that each step forward offers not only new revelations but also even more profound questions. The quest for a theory of everything is not just about synthesizing existing knowledge, but about opening up entirely new ways of thinking. The very nature of the universe, the cosmos, and reality itself may be far stranger and more complex than we have ever dared to imagine. When physicists talk about a unified theory, what they are really asking is, how does everything in the universe come together? How does gravity, which governs the large-scale motions of galaxies and planets, interact with the tiny, probabilistic world of quantum mechanics? How can we reconcile the general theory of relativity, which describes the behavior of space-time on a large scale, with quantum mechanics, which rules the tiny realm of subatomic particles? These are not just theoretical musings, but challenges with profound implications for our understanding of the cosmos. The key to unlocking these puzzles may lie in the strange, often counterintuitive realms of quantum mechanics, where particles don't follow traditional rules. Instead of existing as solid, discrete objects, quantum particles act as waves of probability, existing in multiple places at once and only deciding on a specific state when measured. This concept, known as superposition, is one of the cornerstones of quantum mechanics. It has been experimentally confirmed time and time again through experiments such as the famous double-slit experiment, where particles like electrons behave as both particles and waves, depending on how they are observed. This behavior is at odds with how we perceive the world on the macroscopic scale. When you look at a planet, a car, or a piece of paper, you see something that exists in one place at one time. Quantum mechanics, however, tells us that on the smallest scales, this certainty breaks down. Instead of certainty, we have probability. Particles are more like clouds of possibility than solid objects. But how do we reconcile this strange, probabilistic behavior with the smooth, predictable nature of gravity, which governs the orbits of planets and the bending of spacetime? This is where the search for the theory of everything takes a crucial turn. Physicists believe that if they could understand how quantum mechanics and general relativity fit together, they could unlock the true nature of the universe. They would be able to describe how the smallest particles interact with the fabric of spacetime itself. They might even uncover how the universe came into existence, what happened during the Big Bang, or how quantum fluctuations could have created the entire cosmos from nothing. One of the key insights comes from considering gravity not as a force transmitted through space, but as a curvature of spacetime itself. According to Einstein's theory of general relativity, massive objects like stars and planets bend the space around them, creating what we perceive as gravity. It's not a force acting at a distance, but rather the warping of the very fabric of the universe. In contrast, quantum mechanics suggests that the universe behaves like a vast network of particles interacting with each other, governed by the laws of probability. String theory attempts to merge these two views. In string theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. These strings can exist in multiple dimensions, additional spatial dimensions beyond the familiar three of length, width, and height. In fact, string theory suggests that the universe might have as many as 10 or 11 dimensions, with some of these dimensions being curled up and imperceptible to our senses. By treating particles as different vibrational states of these strings, string theory offers a way to describe the behavior of both subatomic particles and the large-scale curvature of spacetime in a single, unified framework. Yet, while string theory presents a promising candidate for a theory of everything, it is far from being universally accepted. The theory is highly abstract and mathematically complex, relying on higher dimensional spaces that are difficult, if not impossible, to test directly. Some critics argue that string theory is a form of mathematical physics, relying on elegant but unverifiable ideas. Still, its potential to reconcile the forces of nature continues to drive research and innovation in the field. Loop quantum gravity, by contrast, offers a different approach to unifying quantum mechanics and general relativity. Rather than positing additional dimensions, loop quantum gravity suggests that spacetime itself is quantized, that is, made up of discrete units, or loops. These loops are thought to form the smallest possible pieces of spacetime, akin to how matter is made up of atoms. The idea is that at incredibly small scales, space and time break down into these fundamental loops, which behave according to the rules of quantum mechanics. In this way, loop quantum gravity seeks to provide a quantum theory of gravity, one that is fully compatible with the principles of quantum mechanics. What makes loop quantum gravity particularly intriguing is that it offers a resolution to one of the most puzzling aspects of black holes. According to general relativity, black holes are regions of space where gravity becomes so strong that not even light can escape. At the center of a black hole lies a point of infinite density, known as a singularity, where the laws of physics break down. Loop quantum gravity, however, suggests that spacetime does not actually reach infinite density at the center of a black hole. Instead, the quantization of spacetime may prevent the formation of singularities, offering a way to avoid the breakdown of physics at the heart of these cosmic objects. However, like string theory, loop quantum gravity has yet to be experimentally confirmed. The small scales at which quantum gravitational effects become noticeable are far beyond our current observational abilities. While the theory has been supported by elegant mathematical models and has resolved some theoretical issues, its true test will come when we can measure these quantum effects directly. One of the most profound challenges in the search for the theory of everything is that we may not yet have the tools to detect the phenomena that these theories predict. The scales at which quantum gravity operates are so small, close to the Planck scale, where spacetime itself is thought to become grainy or pixelated, that current technology is simply not capable of observing them. As a result, much of this research remains theoretical. But advances in technology, particularly in high-energy physics and observational astronomy, could provide the breakthroughs needed to test these ideas. For example, experiments involving particle accelerators, such as the Large Hadron Collider, LHC, at CERN, offer the potential to probe the highest energies ever achieved in human history. While the LHC has already made groundbreaking discoveries, such as the discovery of the Higgs boson, the energy levels required to probe quantum gravity may lie beyond even the LHC's capabilities. However, future accelerators and quantum technologies may allow us to explore these uncharted realms and test the predictions of string theory, loop quantum gravity, and other approaches. The search for the theory of everything is not just a quest to unlock the secrets of the universe. It is an exploration of the very limits of human understanding. If physicists succeed in finding a unifying theory, it could revolutionize everything we know about space, time, and matter. It might offer explanations for the very origins of the universe, the nature of dark matter, and the mysterious force of dark energy that seems to be accelerating the expansion of the cosmos. It could even provide insights into the deepest mysteries of consciousness and the nature of reality itself. Ultimately, the pursuit of a theory of everything is more than just a scientific endeavor. It is a philosophical journey that challenges our understanding of the nature of existence. As we probe the depths of the universe, we must ask ourselves, what is the true nature of reality? How do we fit into this vast, intricate web of space, time, and energy? The answers may be more profound and more complex than we can even imagine, but they are worth seeking. As we look to the future, it is clear that the search for a theory of everything will continue to drive the frontiers of science. Theoretical physicists will continue to explore new ideas, test new models, and push the boundaries of human knowledge. Perhaps, one day, we will have the answers that so many before us have sought. Until then, the journey itself remains one of the most exciting and profound endeavors in the history of human thought. As we continue this journey toward understanding the universe in its most fundamental form, it is important to remember that the search for the theory of everything is not just about solving one mystery. It's about solving many mysteries simultaneously. Each step forward uncovers new questions, and each answer leads to a deeper understanding of the cosmos. To understand the gravity of this pursuit, it's essential to think about what a true theory of everything could mean. A unified theory would not only combine quantum mechanics and general relativity, it would potentially explain all four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, as manifestations of a single, underlying framework. This kind of theory could, in theory, explain the behavior of everything in the universe, from the smallest particles to the largest galaxies, in a single, unified language. Imagine, for a moment, that we could describe the universe not as a collection of separate, isolated systems, but as an interconnected whole, where all forces and interactions are ultimately expressions of the same basic principles. This is the ultimate goal of physicists working on the theory of everything, to explain everything, from the most minuscule particle to the vastness of the cosmos, in terms of a single, coherent framework. If achieved, such a theory could provide answers to questions that have puzzled humanity for millennia. What is the true origin of the universe? What happens at the moment of a black hole's formation? Why is there something rather than nothing? And perhaps most profoundly, how did we come to exist at all? While string theory and loop quantum gravity remain the most prominent candidates for a theory of everything, there are other approaches that offer intriguing possibilities as well. One such approach is causal dynamical triangulation, CDT, which takes a more geometric approach to the problem. CDT suggests that spacetime itself is made up of discrete building blocks, much like how matter is made up of atoms. These building blocks interact with each other according to specific rules, creating the fabric of spacetime. By treating spacetime as a quantum foam, CDT attempts to model the very geometry of spacetime at the Planck scale. Unlike other quantum gravity theories, which rely heavily on the concept of continuous spacetime, CDT embraces the idea that spacetime might be fundamentally discrete. In this way, it attempts to bridge the gap between quantum mechanics and general relativity. The theory has been successful in certain mathematical models, and its proponents argue that it provides a more natural description of the universe at the quantum level. However, like string theory and loop quantum gravity, CDT faces the challenge of experimental validation. Another intriguing possibility is holographic principle, which is based on the idea that the universe we observe may be a projection of information encoded on a distant surface, much like a hologram. This principle emerged from work on black holes, particularly the Busso-bound and the ADS/CFT correspondence, which suggested that the fundamental physics of the universe might be described by lower-dimensional theories. Essentially, the idea is that the entire universe, with all its three-dimensional complexity, might be encoded on a two-dimensional surface. If true, the holographic principle could radically change our understanding of space, time, and gravity. The holographic principle is a particularly fascinating idea because it suggests that the universe may be much simpler than it appears. Instead of spacetime being a fundamental feature of reality, it could be an emergent property, a kind of illusion that arises from the deeper, underlying physics. If this idea is correct, the theory of everything could involve understanding how the information encoded on these lower-dimensional surfaces gives rise to the three-dimensional world we experience. As we move forward, it's crucial to recognize the potential implications of these theories beyond the realm of physics. The search for a unified theory of everything could have profound effects on our understanding of the universe, and on our own place within it. It might redefine what we consider real, challenging our perception of space, time, and even the nature of consciousness itself. If we can truly unify the laws of physics, we may uncover a deeper, more unified reality that transcends our current understanding. But while the theoretical aspects of this journey are fascinating, it's important to keep in mind that science is also an inherently experimental process. Throughout history, our understanding of the universe has always been grounded in observation and experimentation. When scientists propose new theories, they do so not only based on mathematical models, but also on the empirical evidence gathered from experiments and observations. In the case of the theory of everything, however, the experimental challenges are enormous. Consider the Planck scale, the smallest possible scale of spacetime, where quantum gravitational effects are expected to become noticeable. The energy required to probe this scale is far beyond the reach of our current particle accelerators, including the Large Hadron Collider. In fact, scientists have been searching for alternative ways to test the predictions of quantum gravity theories, such as string theory or loop quantum gravity. These include looking for indirect evidence, such as the behavior of black holes, gravitational waves, and the cosmic microwave background radiation. By studying these phenomena, scientists hope to find clues that will help confirm or refute the various theories of quantum gravity. One promising avenue for experimental verification lies in the study of gravitational waves, ripples in spacetime caused by massive objects moving through space. The detection of gravitational waves in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, opened a new era in astrophysical research. Gravitational waves provide a direct way to probe the fabric of spacetime, and could reveal new insights into the nature of gravity and spacetime itself. In addition to gravitational waves, the study of black holes may also provide crucial information. The event horizon of a black hole, the boundary beyond which nothing, not even light, can escape, represents one of the most extreme environments in the universe. Studying the behavior of matter near a black hole, as well as the mysterious radiation emitted from the vicinity, could yield critical data on how quantum mechanics and general relativity interact. Furthermore, advancements in quantum computing may play a significant role in the development of a theory of everything. Quantum computers operate according to the principles of quantum mechanics, allowing them to perform certain calculations exponentially faster than classical computers. With their ability to model complex quantum systems, quantum computers could potentially simulate the behavior of spacetime at the Planck scale, providing new insights into quantum gravity and helping to test competing theories. Despite these advancements, there is still much we don't know. The search for the theory of everything remains a work in progress, and it's unclear when, or even if, we will ever uncover the final, unified theory. The universe is vast, and our understanding of it is still in its infancy. But the pursuit itself is a testament to the power of human curiosity and ingenuity. As we continue to probe the deepest mysteries of the cosmos, we may discover answers that reshape our understanding of reality, revealing a universe far stranger and more intricate than we ever imagined. The quest for a unified theory is not just an intellectual exercise, it's a journey into the very fabric of existence. Whether through string theory, loop quantum gravity, or other approaches, the search for the theory of everything is one of the most exciting and profound scientific endeavors of our time. Each new discovery, each new insight, brings us one step closer to understanding the nature of the universe, and perhaps, in time, to uncovering the ultimate truth. And so, the journey continues. Each theory, each breakthrough, brings us closer to the day when we may finally uncover the unified laws of the universe, when we may finally understand everything. Until then, the mysteries of space, time, and existence will continue to challenge us, inspiring new generations of scientists, thinkers, and dreamers to look to the stars, seeking the answers that lie hidden in the vastness of the cosmos. As the search for the theory of everything continues, it's important to understand just how profoundly the implications of a unified theory could affect not only our understanding of physics, but also our place in the universe. Imagine a future where the deepest questions of existence are answered, where humanity no longer gazes up at the stars with wonder and confusion, but with understanding. That future may still be far off, but every step we take in this search brings us closer to comprehending not just the mechanics of the cosmos, but perhaps the very reason why it exists at all. One of the most intriguing aspects of the theory of everything is how it might reshape our conception of reality itself. For centuries, we have operated under the assumption that space and time are separate entities. Time flows, space exists as a backdrop, and objects move within it. However, if string theory or another unified approach holds true, space-time may be an illusion, emerging from deeper, hidden dimensions of the universe. This realization could radically shift our understanding of reality, suggesting that everything we perceive as reality may be a projection of something much more complex and unfathomable. For instance, if string theory's prediction that additional dimensions exist beyond the familiar three of space and one of time proves accurate, our entire understanding of space and time would need to be rewritten. These extra dimensions would not be observable directly, but they could influence the fundamental forces and particles of nature, helping to explain phenomena that are currently unexplained. The nature of these dimensions, how they interact with the observable universe, and what they might reveal about the true structure of reality could offer profound insights into the essence of existence itself. While string theory offers a compelling framework, the issue of testing and validating its predictions remains a monumental challenge. To date, there is no experimental evidence that directly supports the existence of extra dimensions or the specific vibrational patterns that are central to string theory. However, the possibility of indirect evidence continues to spur research in both theoretical and experimental physics. Scientists have proposed a variety of ways to test string theory, from searching for specific signatures in particle collisions to looking for clues in the cosmic microwave background radiation left over from the Big Bang. But until we develop the tools to probe the universe at the scales predicted by string theory, we will remain in the realm of speculation. On the other hand, loop quantum gravity presents a very different approach. While string theory introduces new dimensions, loop quantum gravity focuses on the quantization of spacetime itself. According to this theory, spacetime is not a smooth continuum, but is instead made up of discrete chunks, or loops, that form a network, much like the structure of a spider's web. These loops interact with one another, creating the fabric of spacetime. The hope is that loop quantum gravity can reconcile the principles of quantum mechanics with the geometry of general relativity without needing to introduce extra dimensions. One of the key predictions of loop quantum gravity is the idea that black holes may not have singularities at their centers, as traditionally thought. Instead, the theory suggests that the collapse of matter inside a black hole could be stopped by quantum gravitational effects, leading to a bounce, rather than a complete collapse. This idea is still theoretical, but it offers a potential new way of thinking about the behavior of black holes and could provide crucial insights into the true nature of spacetime. The experimental challenges in testing loop quantum gravity are similar to those of string theory. While the theory offers intriguing possibilities, there is currently no direct way to observe the quantum structure of spacetime. However, like string theory, loop quantum gravity could potentially be tested indirectly, through its effects on the behavior of matter and radiation in extreme environments, such as near black holes or in the early universe. The search for evidence of loop quantum gravity remains ongoing, with new experiments and observations potentially offering insights in the years to come. Despite the challenges in testing these theories, the quest for the theory of everything remains one of the most ambitious and important endeavors in the history of science. The implications of a unified theory would be profound, not just for our understanding of the universe, but for the future of humanity. A true theory of everything could potentially unlock new technologies, open up new frontiers of exploration, and provide us with a deeper understanding of our place in the cosmos. For example, the discovery of a unified theory could lead to breakthroughs in areas like quantum computing, energy production, and even space travel. By understanding the fundamental laws of nature at a deeper level, we could develop new technologies that harness the power of the universe in ways we can't yet imagine. This could revolutionize our ability to solve some of the most pressing challenges facing humanity today, such as climate change, disease, and the search for sustainable energy sources. Furthermore, the implications of a theory of everything extend beyond the realm of physics. It could provide new insights into the nature of consciousness itself. If we truly understand the laws of the universe at their most fundamental level, we might be able to answer some of the most profound questions about the nature of life and mind. Are consciousness and the physical universe separate entities, or are they two sides of the same coin? Does consciousness emerge from the physical world, or is it a fundamental aspect of reality? These are questions that have long puzzled scientists and philosophers, and the search for a theory of everything might hold the key to unlocking their answers. Despite the many challenges that lie ahead, one thing is clear: the search for the theory of everything is not just about understanding the universe. It is about understanding ourselves. The more we learn about the cosmos, the more we learn about the fundamental forces that shape our lives. As we continue to probe the deepest mysteries of space, time, and existence, we are not just uncovering the secrets of the universe. We are uncovering the secrets of what it means to be human. The journey toward a unified theory is still in its infancy, and it is impossible to predict where it will lead. But one thing is certain: the search for the theory of everything will continue to inspire generations of scientists, thinkers, and dreamers. It is a quest that transcends the boundaries of individual disciplines and invites us to consider the deepest questions of existence. Whether or not we ultimately find the answers we seek, the search itself will forever change the way we understand the universe and our place within it. In the end, the search for a theory of everything is more than just an intellectual pursuit. It is a journey of discovery, one that promises to unlock the deepest mysteries of the cosmos and reveal a unified understanding of the forces that govern our reality. It is a journey that continues to captivate the minds of physicists, philosophers, and curious individuals everywhere, driving humanity forward in its quest for knowledge and understanding. And while we may not yet have all the answers, the pursuit itself is a testament to the limitless potential of human curiosity and the unyielding desire to understand the universe at its most fundamental level. As we continue on this journey, we must remember that the search for the theory of everything is not just about finding answers. It is about embracing the mystery, recognizing that there is always more to learn, and acknowledging that the universe is far stranger and more complex than we can possibly imagine. And perhaps, in time, the search itself will reveal the most profound truth of all, that the very act of searching is what makes us human. As we venture further into the search for a theory of everything, it's essential to acknowledge the philosophical and existential dimensions of this quest. While many view the search as a purely scientific pursuit, it's important to recognize that the questions we seek to answer are not just about atoms and galaxies. They are about life, consciousness, and the very nature of reality. As we continue to break down the mysteries of the universe, we might find that the answers not only transform our understanding of physics, but also offer profound insights into who we are as individuals and as a species. One of the most fascinating aspects of this journey is how it has evolved over the centuries. If we think back to the early days of science, the idea that the universe could be understood through mathematical laws was unthinkable to many. However, through the brilliance of minds like Isaac Newton and Albert Einstein, the foundations of modern physics were laid, and the dream of understanding the laws of nature began to take shape. Yet even these monumental breakthroughs left us with questions that we still can't fully answer. Newton's laws of motion and gravity served us well for centuries, but as we explored smaller scales, we began to realize that the laws governing the very large, planets and stars, were vastly different from the ones governing the very small, atoms and subatomic particles. The discoveries in quantum mechanics have revolutionized our understanding of the microcosm, where particles behave in ways that seem entirely alien to our everyday experience. However, quantum mechanics doesn't tell us much about gravity and general relativity, which beautifully describes gravity at large scales, doesn't account for quantum effects. This gap, this missing bridge between quantum mechanics and general relativity, is where the search for the theory of everything lies. String theory, as mentioned earlier, is one of the most well-known candidates for a unified theory. String theory proposes that at the most fundamental level, the particles we observe as point-like objects are actually tiny, vibrating strings. These strings can vibrate in different ways, and their vibrations determine the type of particle they represent. This framework provides a potential way to unite all the forces of nature, including gravity, into a single theoretical model. But, as we've seen, string theory has its own challenges, especially the lack of experimental evidence. Despite the elegance and promise of the theory, physicists are still searching for ways to test it in a concrete way. Another approach, as we've discussed, is loop quantum gravity, which takes a radically different route. Instead of adding extra dimensions like string theory, loop quantum gravity suggests that space and time themselves are quantized, made up of discrete units rather than continuous flows. One of the most intriguing ideas emerging from this theory is the concept of space-time itself being granular, like a fabric made up of tiny loops. These loops could hold the key to understanding the deep connection between quantum mechanics and gravity. However, the challenge lies in observing these loops and testing the predictions that loop quantum gravity makes. As both string theory and loop quantum gravity attempt to fill the gaps in our understanding, other theories are emerging as well. Some physicists have proposed the idea of holography, which suggests that the universe we experience might be a projection of information encoded on a distant boundary. This idea has roots in the study of black holes, where researchers discovered that the entropy, or amount of information, inside a black hole could be related to the surface area of its event horizon rather than its volume. This unexpected discovery has led some to believe that our three-dimensional universe might be an illusion, akin to a hologram projected from two-dimensional data. If this idea proves correct, it could dramatically alter our understanding of space, time, and reality itself. Then, there's the potential role of quantum computing in the search for the theory of everything. Quantum computers, which leverage the strange properties of quantum mechanics, might one day be able to solve problems that are currently intractable for classical computers. As we seek a unified theory, these powerful machines could provide the computational power needed to test complex theories like string theory or loop quantum gravity. Quantum computers could potentially simulate the quantum behavior of spacetime, enabling us to explore aspects of the universe that were previously beyond our reach. One of the most exciting areas of research involves the exploration of the early universe, particularly the moments just after the Big Bang. The extreme conditions present at this time may hold the key to understanding how gravity and quantum mechanics could work together. The large amounts of energy present in the early universe could have created quantum fluctuations in the fabric of space-time itself, offering a potential glimpse into the very structure of space-time. Investigating these phenomena could offer invaluable clues about how to unite the forces of nature. On a more speculative front, there's the idea that understanding the theory of everything could lead to technologies that seem almost magical by today's standards. If we truly understand how the universe works at the deepest levels, it might become possible to manipulate space-time itself. This could open up possibilities for faster-than-light travel, the creation of stable wormholes, or even the development of technologies that allow us to harness the very fabric of spacetime for practical use. While these ideas sound like science fiction, they're grounded in the same principles that guide the search for a unified theory. If we unlock the secrets of the universe, we may one day be able to control the forces of nature in ways that seem unimaginable now. While the path toward a theory of everything is challenging and fraught with obstacles, the pursuit of this knowledge is a testament to humanity's unrelenting curiosity. There is something fundamentally human about our desire to understand the universe in its entirety. We are driven not just by the promise of practical discoveries, but by the deep-seated need to comprehend the nature of existence itself. In a way, the search for a unified theory is not just an intellectual pursuit, it's an existential one. The more we learn about the cosmos, the more we learn about ourselves, our place in the universe, and the meaning of life. However, it's also important to recognize that there may be limits to what we can know. As we push the boundaries of human knowledge, we may encounter questions that are simply beyond our ability to answer. The nature of reality might be so complex that even the most advanced theories could only take us so far. But even if we never fully understand the theory of everything, the journey itself will have been worthwhile. It will have expanded our horizons, challenged our assumptions, and deepened our appreciation for the mystery of the cosmos. In the end, The search for a unified theory is about more than just equations and theories. It's about our ongoing quest for understanding. It's about humanity's drive to make sense of the universe and our place within it. And while the road ahead may be long and uncertain, one thing is clear: the pursuit of knowledge is a journey worth taking, one that will continue to inspire and challenge generations to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.